Okay, well, just to recap what we did, we have SSR x2 given x1 is SSE x1 minus SSE x1 x2, or we could write it SSR x1 x2 minus SSR x1. Either way is fine. We don't write SSE x2 given x1 usually. That Yeah, banish that from your mind. You could think of that, I suppose, as the amount of extra error. Um, I don't even know. So let's not even write that. So we only use the marginal notation with SSR. I don't know. I shouldn't have probably wrote that even. It's confusing. The definition extends to any two subsets. We already talked about that. For example, I wrote some here like SSR x4 given those three. So that would be SSE of x1, x2, x3 minus SSE of all four, etc. What could you do this one say? So this one would be SSE. Which ones should be in here? I'll give you a hint. Minus SSE. So this, I just take x1. x1's always in the model. And here I have x1, x2, x3, x4. The next one, SSR. Yep, x1's always in the model, so etc. And then what would MSR be? MSR comes from the extra MSR, that is, so MSR x2 given x1, just write it out using the SSR or the SSE, and you can see what it should be. So in this case, I get MSR x2 given x1. This is, I could write it either way. I can write it SSR x1, x2 minus SSR x1. If I write it this way, I see it's 2 minus 1. So I have SSR x2 given x1. You can see the degrees of freedom is always equal to the number of predictors to the left of the vertical bar. Here, I did it again with the SSRs. You could also use the SSEs. The ends would cancel, and you would get the same number here. So the degree of freedom here is 2. So to get the mean some extra sum square regression, I divide by 2. Okay, the third note is we could have done the test for significance of x2 using t star too. We could use a t statistic as well to do that, but this is because because we do have this t statistic for a single coefficient, but there is no corresponding idea of a kind of t statistic for more than one. If I have more than one, I have to absorb them into models the way we'd use the F test, and consider a full and reduced model, and then use the sum of squares and make the test in the ANOVA fashion as far as variance reduction. So here, this is an equivalent test. We've shown this in SLR that the T and the F are equivalent. They're equivalent too. The only thing is here I can only do it if the test is for one. Is for the significance of one predictor. If I want to test a group being significant, like I have down here, then I can't do it. So to test larger sets of variables, we must use the F test. So for an example, if I add, say, a third column baths, so there I've added x3 with 8 entries to it, and that's the number of bathrooms. It's actually a really good marker for price of house, actually, and it's very simple too. So it's integer, or maybe you have half or something in some of these. And apparently the first one had 4 bathrooms, then 2, 3, 2, 3, 3, 2, 1. And we could add that. So now we could consider SSE x1, x2, x3. I did this apparently. I don't remember now. And I got I got some more reduction. So I think it went from 12.5 to 11. This goes from 11 down to almost 9. So I get it, knock off another couple billion in some squared errors. So my SSR now, if I want to treat x2 and x3 together, because maybe I'm not even sure I want to add x2 yet. So I just want to say, so far x1's in the model. Let's see, are x2 and x3 significant together even? So for this, I'm just going to get an answer for this test, testing whether x2 and x3 are significant together. I'm going to get some kind of answer that's going to tell me yes or no. It's either going to say you can get rid of both of them, or at least one of them is significant, right? So it's not going to tell me which or that I need both, but it's going to say, no, they're not significant, neither of them. Even together, they're not significant. Or it's going to say, well, yeah, they are significant together. And then you could consider isolating whether they both are or one is. So if I do this, I get that number, and then again, I compute F star MSR of the extra sum of squares over MSE of the full model. I did that here, and I get, right. So now the top has 2 degrees of freedom. So you see it's only a little bit better, really, right? And not only that, the bottom one has fewer degrees of freedom too. So it doesn't really help. So what happens is the numerator, it really doesn't change that much. I get a very similar number. And at the same time, the F distribution, instead of being 1 and 5 degrees of freedom, it is now 2 and 4. And I get an even higher threshold under 2 and 4. So again, I'm not even close here. So we have to accept H0. We have some picture like this. And we're out here at 6.95. This is my RR. And we're over here. This is F star. So we accept. Okay, other tests. So not every test, you might get excited and think every test is extra sum of squared. Not every test is extra sum of squared. Consider, for example, the following test. Maybe I want to test, I have 2 predictors, and I want to test whether beta 1 is equal to beta 2 or whether they're not equal. I mean, this might seem strange. It is a little, but could be a test. Okay, I guess in this case, I'm even giving us p minus 1 predictors. And we're just going to say, so we could just use the general linear test approach here, but maybe not extra sum of squares. Okay, so that's the lesson here. The full model, I assume they're not equal, so I have to write it out that way. In the second one, they're equal, so I'm going to write yi equals beta 0 plus beta c for common, I guess. And I will add them together there. And now I can fit, I can always add 2 vectors together, so I can fit the top model and the bottom model. The reduced model certainly has 1 fewer predictor in it, so the degrees of freedom is, so I get n minus p minus 1, right? So that's n minus p plus 1. The other one's n minus p. So in this case, yeah, the degrees of freedom difference is 1. So you get SSR minus SSEF divided by SCF over n minus p, which is F1 n minus p. Again, you have independent chi-squares divided by their degrees of freedom. If you do the proof, you see. And it's F1 n minus p. Okay, another example. Suppose I want to test whether 2 of the betas are exactly equal to 2 and 5. Well, again, I can't really use extra sum of squares, but I can use the general linear test approach here. So I'll make a test, say H0, beta 1 equals 2, beta 2 equals 5, HA, either one of the 2 is not true, they're not both true. And I get a full model that gives me every possibility. I'm only using p equal to 3 here. And then for the reduced model, I just plug in 2 and 5, and I bring that over to the left-hand side, just to be clear. I could absorb it into beta 0 as well, but I think this also works. I make a new yi prime, and then I get a nice SLR model over here, right? Because y's known from the data, and the x1 and x2 are known. So I can just get a new vector on the left-hand side. So this would be f star, and the full model has how many degrees of freedom? Well, the full model has, what am I saying, n minus 4, does that make sense? Yes, because there's beta 0, beta 1, beta 2, beta 3, so that's 4. And then the reduced is 2 less, right? Because I'm assuming that, beta 1 and beta 2 are known, so the actual degrees of freedom of the reduced model is n minus, what the hell is it? N minus 2, yeah. So, or 2 more, I guess. There's 2 more degrees of freedom because I don't estimate those. So I have n minus 2 minus n minus 4, so that gives me 2. All right, there you have it. I will stop this before it gets too big.